Okay, welcome everyone. Why don't we go ahead and get started? I'm JD Smith at the University of Toledo, a member of the PRIMA team. And as you know, we've been holding these PCAST talks to highlight some of the amazing work in the community that's driving a lot of interest for PRIMA and also a lot of the considerations for its design and the proposal itself as we enter the last stage of the PRIMA proposal process. So I'm excited today to introduce Grant Donnelly, who's a graduate student here at Toledo. And Grant has been working on very small dust grains, and in particular, the feedback of AGN on the ISM of galaxies locally, but he's also been thinking a lot about what you can do with something like PRIMA in the high-redshift universe. So yeah, today he's going to tell us a bit more about that, and why don't you take it away?
So first of all, hi everybody. My name is Grant Donnelly. I'm a graduate student at the University of Toledo. And first off, I'd like to thank you for having me on today. I'm very excited to be giving one of the PCAST talks. So today I'm going to be talking about the smallest dust grains in the interstellar medium and why PRIMA will be so important for our understanding of the origin and evolution of these grains. So to get started off, I have an outline with a couple of the major sections that we're going to be talking about today, just to get ourselves oriented. So I'm going to be talking about the smallest dust grains in the interstellar medium, called polycyclic aromatic hydrocarbons, and what they have taught us about and continue to teach us about the local universe. And then we're going to talk about PAHs across redshift, what we currently know, and some of the ways that we're currently constrained by modern facilities to learn more. And then finally, I'll talk about how PRIMA is going to help us close this gap and help us to study PAHs at higher redshifts. But before we get started, I'd like to give some perspective on what we're talking about today. So dust is one of the most striking features of galaxies, and I have an example for you here on this slide. Whether you're looking at it in optical light, like in this Hubble image on the left, and you see the dust showing up as these dark dust lanes in this galaxy and in all galaxies that have dust, or if you're looking at it in infrared light, like you see on the Webb image on the right, where the dust has absorbed starlight and re-emitted it in infrared. So when I'm talking about why I care about studying dust, I just don't want to lose sight of the fact that one of the reasons is that it's just beautiful. So first, I'll talk about PAHs in the local universe and what kind of the ways that we study them and what they have been able to teach us, because that's going to set the stage for why we care about looking at more distant PAHs and in earlier galaxies later. So what are PAHs and how are they different from other kinds of dust? On the left here, I have an image of some dust grains that were captured from the top of the Earth's atmosphere. So this is solar system dust. And in the solar system, it's not uncommon to see these micron-sized grains, like that big one right in the center of the image. But in the interstellar medium, dust grains are typically much smaller. So like 10 times smaller. So a typical one might look like the one that the orange arrow is pointing at, maybe 0.2 of a micron in radius. But the dust that I specifically care about mostly are these polycyclic aromatic hydrocarbons, or PAHs. And these are much smaller. They're more usefully measured in angstrom scales rather than micrometer scales. And their name comes from their chemical structure. They have these carbon rings in a planar structure, and then they have this frosting of hydrogen along the outside. And like all forms of dust, PAHs absorb energy from the interstellar radiation field, and they re-radiate it as heat. This example that I was showing before is primarily PAH light. That's the blue and orange colors here. And we see PAHs in a very wide range of environments. Certainly in most galaxies where we look for them, we will see PAHs, so they're very widespread. You might be wondering about this sort of smoky background that I'm using for my slides here. Although we call them dust grains, PAHs are really much more similar to smoke or soot. So that's why I have this background here to kind of remind us of that. So how do PAHs work? So I mentioned that they're very small grains, and because that's the case, PAHs have very small absorption cross sections. And so in a typical case in the diffuse ISM, a PAH will typically see something like 1 photon per day. And because of that very small size, PAHs also have they have absorption cross sections that are more selective of ultraviolet photons. Small size also means small heat capacity. So when it absorbs its 1 ultraviolet photon per day, that can be enough energy to take the PAH from near the temperature of the cosmic microwave background all the way up to hundreds or even like 1,000 Kelvin. And that is enough energy to excite the vibrational modes of the atoms in the molecule, like you're seeing in this animation here. And as those modes relax, each mode has an associated infrared wavelength that photons will be emitted through. And this eventually gives us the characteristic PAH spectrum that we see. So this plot on the right is from a model of PAH emission. So this is PAH only light that you're seeing. And you see this suite of emission features between 3 and 20 micrometers, these broad emission features that we see pretty consistently in galaxies where we look for them. PAHs are very bright. Here I have an example of like a typical galaxy SED. We'll focus on the red one because that's the one with dust. And what I just want to explain is that those PAHs, which are the broad and very bright emission features between the UV optical contribution from stars and the far infrared bump, they're very easy to observe in most galaxies. Which makes them very convenient for learning about the universe. In fact, they can be as bright as 20% of the total infrared output of a galaxy. So given the wavelength range that we see PAH features emitting through, that's 3 to 20 micrometers, the instruments on JWST are perfect for studying PAHs in the local universe. So here I have a couple of spectra, one on the top right from James Webb NIRSpec, and on the bottom from MIRI, of a galaxy, NGC 7469, showing an example of like a typical mid-infrared galaxy spectrum that you might see. And in these spectra, we see the PAH features very prominently. I've kind of pointed them out with those black arrows there. And this is despite the fact that the PAHs are mixed in with emission lines and continuum and overlapping with each other and extinction features. And then if you were to use a spectral decomposition tool, like for example in this, they're using CAFE, you can see all of those purple broad emission features that overlap with one another, representing the different vibrational modes from PAHs. And so you can just see how many there are and how bright they are here. This is very typical of mid-infrared galaxy spectra. JWST also has imaging bands that are centered on PAH features. So in MIRI, that would be the 770 band and the 1130 band. There's also one for NIRCam at 3.3 microns. And there is a whole body of very important work that uses imaging data to quantify PAH features. And so, of course, the advantages of using images is if you're trying to maximize the spatial resolution or the field of view or the sensitivity, it has those advantages over spectra. And here I'm showing some work that I did that shows that the images for JWST and for previous infrared instruments like on Spitzer do a good job to quantify PAH emission even compared with the spectra. So those are the two bottom plots for two different PAH features. The y-axis there is like a percent difference between the PAH flux that you get from the images using a prescription that we made and the PAH flux that you would get just from spectroscopy. And you can get down to a few percent typically. But there are limitations to using photometry as well. So for redshift, for looking at PAHs across redshift specifically, one of the limitations is that you are forced to look at whatever redshift ranges the PAH features happen to fall within at that redshift window. And even in the local universe, if you can get it, spectra are really ideal for studying PAHs because that is the best way to be able to separate those features from the continuum and from each other, and to be able to study multiple band ratios of PAHs like we'll talk about later. But what I'm trying to show here is that when we get capabilities for far infrared spectra, we really will be interested in using those to study PAH features across cosmic time. So JWST is excellent for studying PAHs. However, Spitzer photometry and spectra really laid a lot of the groundwork. And this is despite the fact that Spitzer has a less sensitivity compared to James Webb. And despite that, it was the first to really make a lot of headway in terms of looking at PAHs across redshift. The Spitzer spectra are sensitive to longer wavelengths, out to 38 micron, compared to James Webb. And it also had a larger field of view and smaller overheads, which added up to making a spectral mapping mode very efficient using Spitzer. If you're worried about the spectral resolution, yes, it was much lower compared to Webb's. But the good news is that PAHs are very broad features, spectral features, and so they're very easily resolved even at lower spectral resolutions. For example, the low-res module for Spitzer infrared spectrograph was 60 to 70. And I have some examples of mid-infrared spectra of galaxies using Spitzer IRS, and you can see that the PAH features have been resolved just fine, even if some fine structure lines are a little bit more difficult. And so when we put all of these things together, what does that maybe remind you of? So I put PRIMA here because I think that PRIMA has some real similarities in this respect: efficient spectral mapping and the similar kind of spectral resolution. But I'm getting a little bit ahead of myself here. And before we move on to some other things that we've learned from PAHs, I just want to mention that the IRS data still has a lot to offer, the Spitzer IRS data, because a whole bunch of it is sitting still in the archive untouched. And I'm involved in a project to give these data sort of a second wind by releasing the full set of spectral mapping mode data as fully reduced spectral cubes. We call the project SIMLA. So if you're familiar with IRS data, you know that backgrounds were very important for reducing Spitzer cubes. So we created a pipeline that will give a custom one to every Spitzer mapping mode observation, and those will all be available. A couple of examples are on the right here. On the top is a mosaic made from SIMLA cubes of the Eagle Nebula. You can see the pillars of creation down there in the bottom left, and then the antennae galaxies are down below that. So this is to say that Spitzer is not done, I think, with its contributions to studying PAHs across redshift. There's still a whole lot more in the archive ready to be contributed. Okay, back to PAHs. So what are some things that they have told us in the local universe? Probably the most typical way that PAHs are used is as a tracer for the star formation rate. And that is because, if you remember, PAHs are very sensitive to ultraviolet radiation. That is sort of their favorite energy range for photons to absorb and then re-emit. And so that makes them good tracers of recent star formation. And as a bonus, the infrared wavelengths that PAHs are emitting their features through is less affected by extinction than UV optical star formation rate tracing methods. And so here I have a couple of examples that are particularly well used, but there are too many to name them all. On the left is from Spitzer imaging. That's the 8 micron band where PAHs are very bright compared with H alpha. And on the right is a star formation calibration from JWST spectra using that same 7.7 micron feature. And you can see the good correlations there. So this is something that is going to be heavily used, I think, with PRIMA to be able to derive star formation rates from galaxies just from the PAH spectra. So speaking of the UV absorption selectivity, PAHs may make their mark on the attenuation curve of galaxies via the UV bump at 2175 angstroms. You can see on the left plot there are a couple of examples of attenuation curves from the Milky Way and the Magellanic Clouds. And that bump at 2175 angstroms is a staple of dusty, high metallicity galaxies. And it is thought that, although it's not confirmed, but the PAHs are probably the main contender for what creates this bump, because these are the range of energies that PAHs really like to absorb. But the emission and absorption geometry differences make it kind of difficult to nail this down conclusively. And on the right, I have one of the first reasons why it was thought that PAHs might be responsible for this bump, other than just their size and absorption cross sections. Those dots are observed attenuation curve, and you can see the bump there. And then the line is a theoretical curve from graphite material, which PAH is pretty similar to, sheets of carbon rings. So even if we can't see PAH emission, the UV bump could be another way that we can study PAHs, especially at high redshift. So let's take a look at this sample of spectra one more time. As I alluded to earlier when talking about where PAHs emit their energy through, one remarkable thing about PAH spectra is their consistency, especially in terms of the central wavelengths that they emit at and the widths of these features, and to some extent their band ratios. But you can see by eye on this plot that, looking at the different galaxies, there are variations in the band ratios, and that is a way to tell things about the environment and the grains themselves, like I'm going to talk about in a minute. But this is one of the most important things that we do with PAHs, is look at their band ratios. And so the way that we can do that is by comparing observed feature strength ratios to those from models. And then we can learn about the environment that PAHs are in and the grains themselves. So I made each of these three animations using recent and a set of recent popular models from Drain et al. 2021, PAH emission models. And these are sensitive to a few different things. So for example, on the left, as time is moving on in this animation, I am changing the grain size distribution by increasing the fraction of large grains and decreasing the fraction of small grains. And you can see that as that's happening, power is shifting toward the longer wavelength PAH features. And the reason for that is because larger PAHs, which are later in the animation, do not get as hot from the same radiation field as smaller PAHs, and therefore they emit more at longer wavelengths. In the middle, I am keeping the PAH grain distribution the same, but I'm changing the input radiation field that the PAHs are using for excitation. And so as time is moving on in this animation, the average age of the stellar radiation is increasing. And so photons go from bluer to redder. And you see a similar thing happening. As PAHs are fed a diet of redder and redder photons, more power shifts toward longer wavelengths because the PAHs are not getting as hot. So PAHs can tell us about grains, the properties of the grains, but also the radiation fields that they're in. And finally, I also want to point out that the ionization of PAHs also impacts their band ratios, and in quite a different way. So in this animation, as time goes on, I am increasing the fraction of PAHs that are ionized in a distribution. You can see that those features at from 6 to 8 micron are particularly impacted by more ionization. So here's one way that PAH ratios have found a lot of, have been applied frequently. And that is in the case of galaxies that have an AGN in them. So when we look at galaxies that are just normal star-forming galaxies with no AGN, PAH ratios will change, but not by factors of more than like 2. Whereas with galaxies that have an AGN, we see very different PAH spectra. And this area is the focus of my thesis, PAHs and AGN. And so if you look in the top right plot, these are some of the earliest mid-infrared spectra of galaxies that have an AGN right in the nucleus. And what do we see? Well, although we see PAHs almost everywhere else in galaxies, when you look at the nucleus of an AGN, it's pretty featureless in the mid-infrared often, and we don't see PAH features there. So this led to the idea that in the face of a hard radiation field, PAHs may not be able to survive and may be destroyed by an AGN. And it gets even more interesting when you look at the band ratios. So that's the plot on the bottom. The y-axis there is a band ratio, the 7.7 feature divided by the 11.3 feature, for blue normal star-forming galaxies and for red galaxies that have an AGN, and as a function of the radiation field hardness as traced by a neon line ratio. And what we see is that the AGN galaxies are offset toward lower values. And remember, those short wavelength features are coming mostly from smaller PAHs. And so the idea is that an AGN might be able to destroy PAHs, but it also might be able to selectively do so for the smaller of the grains. So this is very interesting. If we're able to confirm that this is in fact happening, then AGN are a very important part of the evolution of PAH grains throughout cosmic time. And they play a very important role in that. And so that's something that we're going to want to be able to understand across redshifts. So while we're on the subject of AGN, I also wanted to mention another common use of PAHs. Because PAH features are so consistent in terms of their shapes and central wavelengths, but they're faint near the nucleus of an AGN. The PAH to continuum ratio, or equivalently the equivalent width, is a typical way, a very often used way to identify an AGN. Galaxies that have an AGN tend to have smaller PAH equivalent widths. And this plot here, I believe, is the first paper to do this, where they are showing starburst galaxies and AGN and sort of their PAH equivalent widths, the feature to continuum ratio. And this was one of the first and most important ways that the centers of LIRGs and ULIRGs were studied to figure out whether they were powered primarily by star formation or by AGN or both, because these are typically areas that are shrouded in dense dust. But now the PAH equivalent width is a pretty common way to indicate when there's an AGN in these very dusty environments. And this is another thing that has been and will continue to be exploited at high redshifts. So I wanted to show these animations one more time, just so that they're fresh in our minds, just to really hammer home how much information is contained in these spectra, but also to point out that it can be kind of difficult to pull apart the different things that are going into band ratios. So particularly the left and center animations are showing this. The grain size distribution and the heating from the radiation field are having a similar effect that is kind of difficult to disentangle. And this really goes to show why it is so important to have good models of PAH emission, and so that we can understand the physical processes affecting PAHs so that we can improve and add to these models. And it's also important so that we can use the observations and properly interpret them across time to constrain models and simulations. So here's an example of band ratios in action. One of the common ways that we use them is from these PAH ratio diagrams. So in each of these panels on that right figure, I have band ratios, two different ones, one on the vertical and one on the horizontal. And so that we can kind of try and pull apart these competing pieces. And then on the left is one of these spectral mapping cubes, like I talked about with SIMLA for an AGN galaxy, NGC 4138. And what we did is we extracted spectra in annuli radially out from the center to try and get a gradient of PAH ratios in this AGN galaxy. And the band ratios are plotted as those circles, the colorful circles on each of the ratio diagrams. And so this is a little bit complicated, but I want to walk you through it very quickly. What you're seeing is as the annuli go out, that's following along the arrows of the colored circles, you're seeing the band ratios change. And the way that we try to interpret them is by also plotting them on top of this grid, that's the dashed lines, where each vertex of the grids is a certain place in the PAH emission models. So some place on the ionization fraction, in this case, that's the mu, versus the smallest grain that we allowed, that's the G. That's how we simulate that small grain destruction from the AGN. And so we're able to see here also by showing the colors, which is the fraction of the young starlight, the blue hard young starlight versus the softer starlight from the bulge and stellar disk, that on the left for the smaller grains, we do see some indication that the smaller grains may be being destroyed, but on the right side, you can see that the ISRF, the interstellar radiation field changing, seems to be driving the band ratios there. So a lot going on in these, but I just wanted to give an example of how we can use the PAH emission models to try and disentangle all of these different competing factors. And there's definitely more work to be done in this area. So I've been talking about modeling PAH spectra, but the other kind of side of that is also being able to model and simulate the galaxy properties that go into PAH spectra. And so let me talk about simulations for a little bit. Dust has been a part of galaxy simulations for quite a while now, but they're usually in the context of a simple dust to metals ratio or a dust to gas ratio that is allowed to evolve alongside of other galaxy properties. And that means that SEDs that are generated from simulated galaxies typically have a template PAH spectra put into it, despite all the ways that we've been talking about how PAH spectra can vary. This is just recently changing. So here I'm showing on the left the first ever simulated galaxy in just PAH light, where the PAH emission is totally self-consistent with other simulated galaxy properties. And then the corresponding SED is on the right there. This is using a radiative transfer code called Powder Day radiative transfer for simulated galaxies that incorporates those Drain et al. 2021 PAH emission models that I've been talking about in a way that allows and takes into account all of those different parameters that go into the PAH spectra. So for example, if the simulated galaxy ended up with more small grains versus a different simulated galaxy, that would be reflected in the spectra by showing more power, for example, at the shorter wavelengths. And so this is a very exciting area. And these PAH emission models are an area of very active advancement. So this is work that was just put on the archive a couple of weeks ago to update those PAH emission models. Previously, they were computed for a certain set of radiation fields. And so you kind of had to be able to create a mixing model yourself or to pick one. But now there is code on GitHub. See the PAH spec code on GitHub, and Rishi and Hensley for the work that allows you to create PAH emission models for any radiation field that you want to input. So that's what this animation is showing here, how that's done by computing a whole bunch of different basis spectra that correspond to the PAH emission when the grain has absorbed just one photon energy. These can be used as basic spectra to be able to add up to the whole integrated PAH spectrum that you want to see. So that's some very exciting work. And then one of the other ways that we're applying these developments is to be able to simulate PAH spectra in galaxies that have an AGN so that we can compare with observations. So you're seeing kind of a summary of that on this plot. Each of these spectra are the same Powder Day SEDs in the mid-infrared from simulated galaxies, but we have an AGN in there that is increasing in luminosity as you go up on this plot. And what you're seeing is that the PAH spectra, like we saw in the observations, are beginning to disappear. And so this is an example of how we're going to be able to add in more and more complexity over time to the simulations, and then to be able to figure out which of the factors that change how PAH emission is seen are more or less important compared with the observations. And these will be important for comparing with, for example, high redshift observations of PAHs, where things are less constrained. So the last local universe PAH topic that I want to touch on today is probably one of the most important ones. And it's the fact that observed PAH abundance is very closely tied to the metallicity. And so you're seeing that on, this has been shown in all sorts of different ways, but I really like this plot on the right here, which is for 3 nearby well-resolved galaxies that have strong metallicity gradients. And on the vertical axis there is the integrated PAH luminosity relative to the total infrared as a function of the metallicity, which is on the horizontal axis. And what you see is that at some critical value, I keep in my mind 8.5 and 12 plus log OH, below that value, the PAH abundance drops in accordance with the metallicity. And this similar relationship has been shown in a few different places, like I'll show. But this opens the door for PAH emission to be used as a tracer for metallicity, which is something that is very exciting for high redshift science, to be able to track the buildup and accumulation of metals at very early cosmic times. But not only that, we're also seeing some interesting and important physical mechanism that impacts PAHs at play here. So there's a couple of ideas about this. One long held one is at lower metallicity, where the radiation field is harder and the photons, there's more higher photon energies on average. Are those places where PAHs are being destroyed at low metallicities? Or a more recent idea that's been gaining traction, and one that these authors argue for here, is their inhibited growth at lower metallicities from a bottom-up grain growth process. So when you don't have as many metals around, PAHs are struggling to go beyond smaller sizes and grow up to larger grains. And that is more evident when you look at the band ratios as a function of metallicity. But in any case, seeing how this relationship holds or evolves across time will be very instructive to learn about how PAHs evolve over time and how metals have accumulated in the first place in galaxies. Okay, so we went through a whole bunch of things that we can learn from studying PAHs, but there are still fundamental open questions related to them. And this is my favorite graphic that does a really nice job summarizing things. It's from Caleb Choban at Indiana University. So big fundamental question number 1. What is the dominant mechanism for the formation of PAHs? So dust is thought to originate from AGB winds, but there's a time scale associated with that. And what happens if we see dust too early in observations? Okay, so another idea is type 2 supernovae could create dust also, and they operate on shorter time scales, but the shock waves that they create also destroy dust. And so it's unclear whether or not this is a net positive or a net negative gain over the long run. Wolf-Rayet stars are another idea. We've probably all seen that beautiful image of the nearby one with the dust rings from JWST, but estimates from IMFs that are usually used say that these Wolf-Rayet stars are probably too rare to contribute that meaningfully to the dust production that early on, and they also need a binary companion to be able to produce the dust. Okay, so question number 2. So that's one open question. Question number 2, what are the major processes that act on PAHs as a galaxy evolves? And in order to give us the grain distribution that we see today. So we know that PAHs grow and they're destroyed. And there are many different examples of processes that would contribute to that on this graphic here. But we don't know if PAHs are sort of born small and then grow from the bottom up, or if they break down into smaller pieces after having been created large. So in other words, you can think about that as what is the IMF of PAHs? And what are the effects of an AGN turning on and off, like we discussed? So simulations are going to be very important for us to try and understand this, but we also need to be able to compare those with observations. So the ability to evaluate PAH abundance and feature ratios throughout time is going to give us a much better idea of which of these processes are at work. Okay, so this brings me on to part 2. PAHs at high redshift. I hope you agree that what we've talked about so far is all kind of pointing us toward the ability to study PAHs across high redshift. So here's a quick summary. I'll go through this very quickly. Why study PAHs at high redshift? We want to be able to track the buildup of metals. We want to be able to understand the processes acting on PAHs. And these are both going to serve to constrain models and simulations. And we're interested in using them to study other things like star formation rate or the abundance and strength of AGN throughout time. So here are some examples of some of the first detections of PAHs at high redshift using Spitzer. So on the left is the number density of detected galaxies as a function of redshift. And as you would expect, there are a whole bunch of galaxies detectable in the local universe, but as the redshift increases, you see less and less galaxies, except for this bump at around redshift of 2, where the 8-micron PAH feature, which is very bright, has moved into the 24-micron filter of Spitzer, which they were using to detect these galaxies. And you all of a sudden see this big increase of galaxies. So is that a real increase? Probably not. But it just goes to show that PAHs are so bright that they can impact the number densities of galaxies. And that's going to be something that's very important for PRIMA too, as PRIMA uses these these very bright PAH features to be able to detect galaxies. And then on the right are a few of the best Spitzer spectra of high redshift PAHs. They're all shifted back into the rest wavelength, and that's the data. And then you see it compared with the solid smooth line, which is a PAH spectrum in the local universe. And these are all from around cosmic noon, so around redshift 2. And so what do we see here? The PAH spectra are not all that different from what we see in the local universe, and they're very bright by redshift 2, which you see on the left plot also. So just a few billion years after the Big Bang, we already have some evidence that PAH spectra and therefore the grain distributions are probably pretty similar to what we see in the local universe. So continuing on with this theme, this is, to my knowledge, the current record of the most distant PAH detection from just PAH emission feature spectra. And it's at redshift of 4.22. It was detected in a Miri cube. But you have a Miri cube, but the detected feature is the 3.3 micron feature at rest. So we're seeing PAHs at about 1.5 billion years after the Big Bang here. And the takeaway is that, again, the PAH feature is pretty bright in this galaxy already, and you see it in a binned way in the purple spectrum on the right plot. And that's compared also with a more nearby galaxy, VV114. It's not all that different. The equivalent widths are for this PAH was very high, and it's pretty bright. So once again, we see pretty normal PAH emission so early on. But I need to mention that this galaxy is strongly lensed. That's why it has that ring shape in the Miri cube there. And that is the reason that we have such signal to noise for the spectrum. So this is, and I want to emphasize this, probably about the limitation. This is really pushing the limits for what JWST can do in terms of looking at PAH emission features in spectra. Okay, so on top of that, let's return to the PAH metallicity relationship. What do we know about this outside of the local universe? I've put that same Whitcomb et al. Plot on the right here for our reference, but on the left, we have a similar measure. It's one PAH feature over the infrared luminosity as a function of the metallicity, but the metallicity axes are flipped between the two plots. And the blue dots are for local galaxies, so you see a similar kind of relationship. But then the orange hexagons are stacked observations from galaxies at around cosmic noon. So we have some evidence building that the PAH-metallicity relationship may already being established by this time or earlier. And so from all these things that I've shown you so far, the takeaway, I think, is that PAHs appear to be quite like PAHs at around cosmic noon and a little bit earlier appear to be quite like what we see in the local universe. So whatever things have been acting on PAHs have been established relatively early. So what about simulations? Here I'm showing some work in progress of how simulations compare with the PAH-metallicity relationship. And let me just remind you that PAH simulating is a very, very young field. But already in this example, the simulations seem to be doing a pretty good job. So for the simulated galaxy, those colored squares, they at about redshift 2, which is sort of purple or dark green, that's about the place that we see the PAH-metallicity getting established, PAH-metallicity relationship being established. And you can see that that is where the simulations begin to agree with the data. And then they give us some indication of what might be happening at earlier redshifts. So this is a very exciting development that's happening, and we're all excited to see more about this. But work like this tells us, do we understand the physics driving the PAH-metallicity relationship? Can we make predictions for what we see when we have PRIMA and we can reach even further back in cosmic time? So here are a few examples of what observations are currently telling us at like the very limitations of what we currently have across redshift. On the left, we have a sample of galaxies at around cosmic noon, and there's ages of the galaxies derived from best fit SEDs. And even though all these galaxies have sort of similar metallicities, the younger galaxies with an age of less than a gigayear have a factor of 3 lower PAH luminosity compared with the older galaxies. So this may be evidence of seeing a delayed injection from that timescale associated with AGB winds. And on the right is a very high redshift but very clear detection of the UV bump at redshift of 6.71. So if the UV bump is from PAHs, and this is one of the highest redshift detections of PAH. And the strength of the bump that is already seen at these very early times, while this galaxy that they detected it in does not have all these old stars, it could be evidence that there needs to be some faster method of dust production than the AGB stars that are often thought of as the main way that dust and PAHs are produced. But again, these are very interesting, but I just want to point out that we don't really have a very clear picture yet of what's happening with dust, especially in the first billion years after the Big Bang. Okay, so I'll go through this very quickly so we can get on to PRIMA, but just a summary of what we know about PAHs at high redshift. The current limitation from JWST is around redshift 4. Which is a 1.5 billion years after the Big Bang. We don't have much to say about band ratios yet, in large part because we're limited to photometry. And so to move forward, what we're going to need is multi-band far infrared mapping so that we can see those PAHs at high redshifts, and especially spectra. So with all this in mind, let's talk about PRIMA. So first, I have the main science themes graphic from PRIMA here, just to point out that all the things that we've been talking about are central to the stated science goals of PRIMA, especially this one on the bottom, buildup of dust and metals. PAHs are specifically pointed out here. But also argue that this second one, evolution of galactic ecosystems, PAHs are going to contribute significantly to that as well by helping to trace the star formation and the metallicity of early galaxies, and also to be able to track AGN abundance and strength based on how PAHs are used as an AGN indicator across cosmic time. And you remember that comparison that I made to Spitzer around the beginning in terms of PRIMA being able to efficiently spectrally map large areas? I think that the logical conclusion of that comparison is that PRIMA is poised to do for high redshift PAHs what Spitzer did for PAHs in the local universe, which is to say, be completely revolutionary for that science. So PRIMA, in terms of wavelength ranges and sensitivities, picks up where Spitzer and JWST leave off. So on the left is a plot that I made just looking at how much PA power you get in certain instrument wavelength ranges for JWST versus PRIMA as a function of redshift. And you can see it around redshift 2, which is where our current best knowledge of PAHs at high redshift comes from. That is the place where PRIMA really starts to pick off. So it's a very complementary instrument to, or complementary facility to JWST. And at redshift 4, which is our current best JWST PA spectrum, there's practically no PA power left there. Whereas at PRIMA, I mean, it's almost all of the PA power is within the PRIMA window there. And so on the right plot is another way to see this. It's a PA spectrum being shifted across redshift with respect to the Firis bands and sensitivities. So this is important. Not only are we looking at PAHs very early on, the wavelength ranges that we'll have sensitivity to allows us to see PAHs across time. And so for at least the brightest galaxies, we'll be able to quantify PA abundances and also get the band ratios that we learned so much from the spectra from just a few 100 million years after the Big Bang and across cosmic time all the way up to cosmic noon. And so this is right about the right time for us to be able to evaluate dust creation mechanisms and what mechanisms are important for dust growth. So we put in one of those PRIMA proposals in the geoscience book as an example to do the sort of logical thing for tracking PAHs throughout cosmic time using PRIMA's instruments. So it's 2 steps. Step 1, use Primager for what it's good for. Look across a large area, locate galaxies that are bright in PA for follow-up with a more targeted campaign with Firis to get that PA spectra. And then on the right, we're just showing some ideas for how PA abundance might increase over time, but really just to highlight that there are all kinds of scenarios that are not well constrained. And so this kind of program will, I think, be one of the first things that we'll want to do, just to build up that sample of spectra and PA-bright galaxies throughout time. Both of PRIMA's instruments will be used to collect data for PAHs. Like I mentioned, Primager has that large field of view, good sensitivity. So in a very reasonable amount of time, a large number of galaxies will be able to be detected across a wide range of redshifts. And then I have some more simulated Firis spectra here, just so you can see how good Firis will be as an instrument for looking at PAHs. Even better example on this next slide here. On the left plot, I have 2 examples of simulated Firis spectra. One for the red one has a PA abundance that's QPA, very similar to what we see in the local universe. You see those PA features, very bright, very obvious. And with a spectral resolution from Firis that is even better than, or higher resolution than what we had with Spitzer IRS. With the low resolution module that was usually used for the science. So I just want to emphasize again how well tuned PRIMA will be to look at PAHs. So you have that Spitzer spectrum there for comparison. I also want to mention that on the left plot, those dots there, that's the simulated hyper spectrum from Primager on top of it. And if you were to take away the Firis spectrum, I think that you would still be able to pretty accurately quantify the PA features there. And so even for the galaxies that we aren't following up with Firis, we'll still get pretty good PA abundances from just Primager, again, very efficiently. So while I'm wrapping up here, I was looking through the that same Geo book, which, by the way, there's a second volume now. If you have not seen it, I recommend going through that. I was just going through and seeing what other ideas that people had for using PAHs with PRIMA. And not surprisingly, several of them mentioned using PAHs as a star formation rate tracer and to be able to detect galaxies. Here's a nice example of that, where they modeled how many different detectability limits as a function of different spectral features to use for the detection. PAHs were a particularly sensitive one. And then just a few more examples, people talking about the PAH-metallicity relationship, those doing good quantitative science on that across redshift. Those are the top two examples there. Tracing and finding AGN using the PAH equivalent width was another popular one, really taking advantage of just how bright PAHs are. And then one that I'd really like to highlight is this one on the bottom here. The idea of using PRIMA in conjunction with SphereX that has the 3.3 micron feature in it to do what they call feature intensity mapping. So it's similar to line intensity mapping using PAH emission. And so PRIMA will be able to create these feature intensity maps across, like three-dimensional maps across redshift, without having to actually individually detect galaxies. That's an idea I'm very excited about. They have a whole paper on the idea also on AppJ, so I highly recommend taking a look at that. So I'll leave you with a summary here very quickly. We talked about PAHs and how they're used in the local universe. They're very useful tracers of galaxy conditions like the metallicity, like finding an AGN and tracing the star formation rate. But we need a better understanding of the origin of PAHs and the processes that act on them as they evolve. And that points toward our need to be able to look at them across redshift. But current high redshift studies are limited to the current facilities that we have, which are amazing, but not necessarily optimized to do this kind of science like PRIMA will be. And yeah, PRIMA will be positioned to just revolutionize PAH science outside the local universe. So I'm happy to take any questions now. Thank you very much. I'm very happy to be here doing a PCAST talk. So thanks again.
All right, thank you, Grant, for a great talk. Time for a question or two. If anyone wants to unmute, please go ahead. Doug.
Yeah, so I'll ask a quick question if I can. That was a wonderful summary and a great talk. I really, really appreciate it. You said something that I should know given my age and everything, but I wasn't entirely aware of, and that is that it's not just that the PAH emission is responding, but it's actually that emission that we're seeing is actually as it releases the energy, and so there is a time dependence. Is that correct? If I were to watch an individual PAH, I would see those lines vary as it re-equilibrates down to the lower temperature. And therefore, does that make the modeling of PAH emission even more complex?
Yeah, that's a very good question. But the short answer is no, that time scale is very short. So if you had like a laboratory condition, you would be able probably to measure the relaxation time of the PAH after it's been excited by a photon. But astronomically, we can't do that. This is like on the order of seconds, I think.
I understand that part, but I guess what I was wondering is whether or not it therefore meant that we needed to model them more carefully because we need to understand how that spectrum is coming out. Not that we would see it in time, but that is important to what the spectrum is.
I see. Yeah. So I still think that the answer is no, because those PAH emission models that we see, those are integrated over that entire time. I guess so the way I'll answer the question is to answer how the models are created currently. When I show those PAH emission models like I was, that spectrum is the integration over the entire amount of time that the PAH has had to re-emit that energy. Yeah. And Because of the fact that the PAHs are sort of stochastically heated 1 photon at a time under normal conditions, that time scale of the relaxation, when we're looking at like a very large area of, like kiloparsec scales, for example, I don't think that the relaxation time is going to really change how the observations need to be interpreted. But it is an interesting point.
Okay. Thanks.
Mm-hmm.
Okay, well, I think we're out of time for additional questions, but please get in touch with Grant if you want to learn more. Thank you all for attending. This will be the last PCAST for the year, but we are resuming next year in, let's see, late January, I believe the 26th, with Meredith McGregor. So please look forward to that. And otherwise, have a great holiday, everyone.
Thank you, everybody, again.